we're doing in this course is being able to describe the movement of a rigid body. Okay, and this is going to be the most important thing. It'll come again and again, is coordinate frames. Okay, so we'll always assume there is a frame which is fixed to the world, does not move. That's the world frame. It's denoted as OO, XO, YO, ZO. The 0 represents that it is the world frame. So when I put I equals 0, that would be the world frame. It's also a fixed frame. It will not move. It sort of serves as a frame of reference about which we can describe the motion. And then when I is greater than 1, so 1, 2, 3, we'll use those frames to be the body frame. Okay, I'll get to what I mean by body frame in just a bit. This frame is actually attached to the body and moves with the body. So what I mean by that is, if I have a rigid body like this, okay, so you can see I am going to put one of the corners at the origin, and when the body moves, that frame will actually move. So that is, it's also called the body frame or the moving frame. And then the frame basically is attached to the body and moves with it. Again, so when I say I equals 1, 2, 3, you could have multiple bodies, and each body has a frame. It will move with it. In case of robotics, what we'll have is multiple links. Let's say arm has 2 links. Then each link would have its own coordinate frame. So I will be 1 for one of the link, and I will be 2 for the other link, and then we'll basically use that to describe the movement. So that's kind of the most important thing. Now with that, let's get into how we describe movement, which is essentially 2 things. One is translation, and another one is rotation. Okay, so translation is basically when a body moves without undergoing any sort of rotations, right? So it's just movement in the X, Y, Z direction. So here I'm going to show the world frame. And let's say that we move the body, and then the body has its own reference frame. And here it's just translated to a new point. So X1, Y1, C1. And just to make it easy, though I've shown X, Y, Z, I'm just going to assume that things move in one plane, so XY plane, and then of course you can extend that to Z plane too. So this is clearly the origin of frame 1, and then origin of frame 0. Okay, we'll use X0, Y0 to describe the translation of the origin. And then if you have a point C, and that point C could be some point in the world, let's say that point does not move, then you can describe the position of C with respect to frame 1. You could also describe it with respect to frame 2. If you describe it frame 1, then we'll call that distance as X. I did a mistake here. This should be swapped. This should be Y0, should be X0. So this should be X or Y0, sorry, Y1, and this should be X1. Let me just blow this up. Now to distinguish it from any other point, what I'll do is I'll abbreviate this as YC and XC. So that way it's very clear that's the X position of point C, and in frame 1. Okay, so you could also describe the position of point C in frame 0. So in this case, this distance, it's too much clutter. So this is going to be y of point C in frame 0. And then similarly, there will be x of point C in frame 0. Okay, so that's just getting used to the vocabulary we'll be using in this course. Okay, so when we write the position of point C, we can write it with respect to frame 0. So here I'll use x C0, y C0, and then I've not shown any movement in the z direction, but you could have motion in the z direction too. So z C0. If you want to describe it up in frame 1, it would be x C1, y C1, z C1. Okay. Now here's one. Let me just. This should be O. This should be O1. Okay. Now the reason I wrote it as O and O1 is because what I'm going to do is I'm going to use the superscript to describe the frame. So I don't really want anything to be on the top. So let's call that O1 with 0 and 1 is the subscript. And so what I can do now is if I want to describe the location of point O1, so it's this point, I have to describe it with respect to some frame. So in this case, I'm interested in describing it above frame 0. So that goes up. And you can see from that figure, the way I've drawn it is that its x coordinate is x0, y coordinate is y0, right? And then let's say there is a z coordinate, which I've not shown there to avoid clutter. It's going to be z0. You could also describe the position of point O, that is the origin of frame 0, with respect to frame 1. So this is what's the distance of this point with respect to O1. And you'll see that it's nothing but the negative of x0, y0, z0. Okay, so the key thing here is that the part in, I'm going to show in pink, is the frame of reference. Okay, so this will come again and again. So just be mindful of that. Okay, let's get to rotations. Okay, here we will show the same caricature O X X O Y. I will just call it X subscript. Okay, so that's the frame. What we do is similar to translation, where we take the moving frame and we just translate it. Here we'll take the frame and rotate it. So there is another frame on top of this frame, which is actually on superimposed on frame 0. So what we'll do is we'll rotate this, and then the rotation I'll show like so. Okay, now here when we did the rotation, we actually rotated about the z-axis. Okay, so the way to think about this is that if you take the right hand and if you point your thumb in the direction of the frame of the axis z, then the rotation is given by your curled fingers, right? Like that. So this is rotation by an angle of theta about the x-axis. Okay, so the same thing goes here. Let's say if we have a point C and we want to describe its position. By the way, here the origin does not change, right? OO and O1 are the same origin because we never translated anything. Okay, now we have a point C and we want to describe the position of point C. There are two ways of doing this. One way is we drop perpendiculars to the axis. Okay, so you can describe the position with respect to frame 0, or you could drop perpendiculars to axis x1 and y1, and that's another way of describing the position. So let's say that for our notation, this distance is y of c in frame 1, and then this thing is x of c in frame 1. Okay, and then I could also, well, let me just write it down. So we could also have, this would be x of c in frame 0, and then this would be y of c in frame 0. Okay, now there's a there's a way you can write the position of c in frame 0 as a function of xc1, yc1, and that's basically a trig calculation. I'm just going to write it down. Xc0 is actually given by cosine of theta xc1 minus sine theta yc1. The way you'll do this is you'll take this xc1 and then you'll find its component in the x0 direction, and then you'll find the component of yc1 also in the direction of x0, and then you'll see that if you take cosine and sine and subtract the way I've written it down, you'll get the distance xc0. Similarly, you can write yc0 as sine theta xc1 plus cosine theta yc1. Okay, so now what we'll do is we'll write this as a matrix. And by the way, you can also write zc0. It's just going to be zc1, right? It's not going to change because the z is not going any movement. So let's write this as a matrix: xc0, yc0, zc0. I'll separate out all the cosines, sines, and then write it as a function of xc1, yc1, zc1. So you can see that it will be cosine theta minus sine theta 0, sine theta, cosine theta 0, and 0, 0, 1. Okay. Yeah.
We were looking about the version. I don't think that would change the right x and y.
X and y will change. Z will not change. Yeah, that's why we have this.
But that's so when we rotate about, it doesn't change. But if we were to rotate about the origin, how would that change?
So when you rotate, you only rotate about an axis. There's nothing like rotating about well, point, right? You need some axis. So the way you do this is you look at take your right hand, you point your thumb in the direction of the axis about which you rotate, and your direction of your fingers, your remaining fingers, not the thumb, gives you the direction of motion, which is positive, of course. Yes, it's always, we always accustomed to 2D rotations, which is actually 3D. It's actually always rotation. We always assume it's about an axis pointing out of the plane of paper. So this is actually, Z is actually pointing out of the plane of paper. Okay, so I wrote this down, but the shorthand notation of writing this would be C0 equals R, now pay attention to this. This is rotation of frame 1 with respect to frame 0. So rotation of frame, what's the convention I used? Okay, that's always frame. Okay, so So what I've written down here is, this is the position of C in frame 0, which is the fixed frame. This is the position of C in frame 1. And then the way you can relate them is through this rotation matrix R, which is of that form, cosine minus sine. It's a 3x3 matrix. Okay, and we'll get to multiple rotations. Okay, that is coming in the next part when we talk about Euler angles. But right now, just focus on one rotation about one axis. Okay, so let me expand on that. Let me write it down first. You'll have it in your notes. So R10, C1. This thing here is rotation of frame 1 with respect to frame 0. Okay, now if you were to reverse this, that is, if you were to do C1 equals R10 inverse C0, that's just what I did here was I just multiplied both sides of the first equation by the inverse of R10. And if you take the inverse of R10, you'll see that it comes out to be, so you need to take this equation here and take its inverse. Okay, and it actually comes out, it's very interesting that it comes out to be cosine theta sine theta minus sine theta cosine theta 0, 0, 0. Okay, so if you see this equation, you see this form, all you see is that the negative has been moved from over here, it's in row 1, column 2, right? The negative is here. It's moved to row 2, column 1. So really, this is what I've written down is actually the transpose of what was written here. So this is C1 equals R10 transpose C0. Okay, so this is like the best part about a rotation matrix is this thing, which is if you want to change frames, all you need to do is take the transpose. Okay, so in other words, you could also, in our terminology, where we write C1 in terms of C0, we write it as R01. So note that this is the opposite of what we had earlier. This is just a notation which says that if you want to write C0 from world frame to the fixed, from world frame to the body frame, then you just swap this. So this we found is same as, this is the same as this, right? So if you want to find what is the rotation of frame 0 with respect to 1, it's nothing but R1 with respect to 0 transpose. So you can write one frame with respect to the other frame with respect to 1, and the relation is basically just the transpose. Okay, this makes our life easy. Okay, so with that, we'll go to the next part, which is now we have figured out what translation does, how we can write translation. We know how rotations work. We can combine the two and do combined rotation translation, and that's where we're really heading to. Okay, so here we have our world frame, which is fixed. I'm just going to create a temporary frame, which is a translated frame. And then once we translate it, so this will be some temporary frame. So let's just call it X1, I guess, Y1. I could have called it 1 and then the second one 2, but let's just call it bar, so that way we don't really have to worry about having another name for it. So let's just say that's what moves, and then it rotates. So we have x1, y1, and then z1. So we have OO, OO, XO, YO, ZO moves to, this will be O1. Let's put a bar here. Bar X1 bar. And then finally O1, X1, Y1, Z1. Yes, so the way to write this is X0, Y0, Z0 equals, sorry, X. Let's just consider point C as usual. So this would be XC, YC, ZC in frame 0. Okay, it consists of the motion of the frame itself. So let's say that the frame moves to a point, this point here is X0, Y0, Z0. That is the translation part. So I'll write down X0, Y0, Z0. And then there's the rotation part. So cosine theta minus sine theta 0, sine theta, cosine theta 0, 0, 0, 1. And then this is going to be XC1, YC1, CC1. Okay. Translation, rotation. Okay, so the way to write it in a single line like before, we wrote C0 is what? So C0 is going to be O, this is O1. Well, actually O1 bar is the same as O1, 0, right? So this is going to be O1, 0. That's the motion of frame 1 with respect to frame 0. So this point is that. And then the second part is R1 with respect to 0, the rotation, and then C in the body frame. So that is the formula which we would use. Okay, now this formula is kind of, I think it's well known. You might have seen this before. It turns out that this formula is actually kind of unwieldy because when you try to use this, so let's see how to do this. So when you talk about multiple rotations and translations, so assume that there is body, so there's one body that's so this will occur, for example, in a manipulator. Okay, so we would have frame 0 here, we'll have frame 1 here, frame 2 here, frame 3 here, and then you can keep going. So what we have to do here is when we are describing the motion of, say, this manipulator, we will essentially go attaching these frames to each of the joints like this. Okay, so we've attached these frames, and then what we want to be able to do is, so normally what happens is the motion of this frame is described with respect to the frame 0, and then the motion of frame 2 is described with respect to frame 1, because what we do here is we specify the relative angle between frame 2 and frame 1, and then finally we'll have motion of frame 3. So we'll have to keep applying this formula recursively from frame 0 all the way to frame 3. So in this case, what we'll do is we will have x0, y0, z0, O1, x1, y1, z1, O2, x2, y2, z2, and so on. So how do you use the formula? Well, you use it this way. We wrote this down some time back from frame 0 to 1. We write the same one for frame 1 to 2, R to 1, and then frame 2 to 3. Yeah, now, and what we want to eventually do is we want to be able to describe, for example, this frame. Like eventually, we are always interested in how the hand moves or the gripper moves with respect to the world frame, right? Because maybe it's manipulating an object in the world frame. So in order to do that, we need to recursively go from frame 3 to frame 0. So for that, we essentially we can substitute this C1 inside here and this C2 inside here, and that will help us relate frame C0 with C3. So this frame with respect to 0. So what happens here is when you do this, you get O10 plus R10. C1 is O21 plus R21 C2. And then I'll repeat that step again. R10, R21. C2 is O32 plus R32 C3. See, so O10 plus R10 plus O21 times O21, R10, R21, O32. And then R10, R21, R32, C3. Okay, so now we have this part is the translation part. As you can see, it has all the origins coming in it. And then this part is the combined rotation part. Okay, now this, you could take this and go with this. And then if you have like n links in this, just formula will just blow up. And it is not a very efficient way. Well, it is, I think it is fine to do it, but I think it's just that there's a better way of writing successive translations and rotations in one form. So we'll actually not deal with, so these are all 3 cross, so C0 is 3 cross 1, right? And then this is 3 cross 1. And then when you do this multiplication, you get 3 cross 1, right? This is 3 cross 1, this whole multiplication with 3 cross 3. So what we'll do is instead of trying to represent motion as combined translation and rotation using a 3 cross 1 matrix, we'll actually use a 4 cross 4 matrix to do combined rotation and translation, and that will make our life much easier, as you'll see. So this is the formula for 2 frames. I'm going to show you a much better or a more compact way of writing the same formula. Okay, so that is what is known as a homogeneous transformation, and it will be the central part of everything we do with in this course, homogeneous transformation. We'll use them extensively. Okay, so the homogeneous transformation is something which is used to relate frame I with respect to frame I minus 1. So R1 with respect to R0 or R2 with respect to R1. It has this form, Ri I minus 1, Oi I minus 1, 0, 1. Okay, so let me elaborate on what this is. So the rotation matrix is the same 3 cross 3 matrix. So we wrote down a rotation matrix here. That's 3 cross 3. So that would be 3 cross 3. Okay, the vector O is basically what we wrote down here. It's maybe this is the best way. So this is the vector. It's a 3 cross 1 vector. So this is 3 cross 1. So now what we have here is a block matrix. So we need to combine a vector and a rotation as follows. So this is sort of like a placeholder that actually has 0, 0, 0. So this block is 3 cross 1, sorry, 1 cross 3. I will not write it as 0, 0, 0 henceforth, but you have to understand it's 1 cross 3 just to make this homogeneous matrix work. And this 1 is 1 cross 1. So if you look at this matrix, there are 3 rows plus 1, 4 rows. And then if you see the columns, there are 3 plus 1, so 4 columns. So this homogeneous matrix is 4 cross 4. Okay, so that's the definition of homogeneous matrix. Why do we want it? Well, it turns out that you can actually write combined motion, translation, and rotation like this clunky formula using just that homogeneous matrix as follows. So if you have C I minus 1 equals HI I minus 1 CI. Okay, so this C is actually different from this is, let me call that a, it's difficult to see this, but let me call this a uppercase C. It's different because this C, what we'll do is we'll write it as the small c with a 1. Okay. So this C is what we wrote earlier, XC, YC, ZC in frame I. Same for this one. This 1 is actually a placeholder. It'll actually make the multiplication work out because what we have here is a 4 cross 4 matrix. This is a 4 cross 1. This is 3 cross 1, right? So 3 and 1, and then 4 cross 1. So when you do this, all works out. So this, if this is not clear, it will become clear in just a bit. Okay, so let me show this to you, what this looks like, how this connects with this formula, C0. Okay, so this formula we got, and we don't question that because it came from our derivation of combined rotation translation. Let's see how the homogeneous matrix helps us to write the same formula in a very compact way. Okay, so here's, let's say that we have motion from frame 0 to frame 1. When I say this, it really means OO, XO, YO, ZO to O1, X1, Y1, Z1, just a shortened notation. So we'll write C, remember it was CI minus 1 equals HI, I minus 1, CI. So this will be C0 equals H10, C1, right? I equals 1. Okay, so what is C? This C is a uppercase C. So the lowercase c and 1, as I wrote on earlier, R10, O10, and then I wrote 0. This is basically 1 cross 3, but I'll just write it as 0. And 1, and then C1, 1. Okay, so when I take the matrix multiplication on the right-hand side, okay, this you can, even though it's a block matrix, you can think of the multiplication just like you would think of a matrix multiplication. You need to take the first row, multiply it with the column C1, 1, and keep going that way. So R10, C1 plus O10. So this is multiplied by this. So that's the first term. This is multiplied by that second term. And then this 0 is multiplied by C1. So that's 0. 1 multiplied by, no. Yeah, 1 multiplied, 0 multiplied C1 is 0. 1 multiplied by 1 is 1. So 1. So let me remove the clutter. So this will come out to be just that. Okay, so there are 2 lines. Really, there are 3 lines. The top one is 3 cross 1, right? And this is 3 cross 1. And this is 1 cross 1, 1 cross 1. So what this second part, the second line is saying is that 1 equals 1. And that's no doubt correct. So that's just, you can ignore that, but that is just saying that 1 equals 1, which means that the multiplication is just a placeholder. It just makes the multiplication make sense with a 4 cross 4 matrix. But really what we're after is the first row in that. The first row is C0 is R10 C1 plus O10. That was basically the formula we wrote down earlier. It is this formula, exactly that. So the homogeneous transform was able to represent movement from frame 0 to 1. Okay, and this is in agreement. Now, let me go a step further and show what happens if you go to do one more rotation translation. So frame 0 to 1, 1 to 2, and then you'll see that this form actually helps us a lot. So now let's do frames. Here's the second example. Let's go from 0 to 1, and then 1 to 2. So we have C0 is H10 C1, and then C1 is H21 C2. So from this, we will eliminate C1. So we can substitute this C1 here as H21 C2. Okay, so let's write that down. This is C, the lowercase C0. H1 is R10, O10, 01. H21 is R21, O21, 01. And C2 is C2, lowercase c, 1. Okay, now we can do the multiplication. It's actually on the right side. It's much easier to do the vector with the matrix first and then do the second one. So what I mean by that is keep the first term as is. And let's do the multiplication here. So R21 C2 plus O21 times 1, and then 0 times C2 plus 1 times 1 is going to be 1. Okay, the next step is we do the same multiplication of 2 cross 2 times 2 cross 1. And this is 2 cross 1, this is 2 cross 2. Okay, again, this is not actually 2 cross 2, it's actually 4 cross 4, but the way it's written in block form, it just makes it easier to think of it as 2 cross 2 and 2 cross 1. So now we can do R1 times R10 times R21 C2 plus R2 Okay, so what I did here was the first time I took this and I multiplied it with both, and so I got that. Next, I take this and I multiply with O1. So that would be the additional term, O10. Okay, next, I take the 0, multiply with this whole. This 0 is multiplied with this thing, so that's 0. And then this 1 multiplied 1. So 0 plus 1 is 1. So I'll end up with 1. So we have C0, 1. And so the second line is just saying that 1 equals 1, which is obviously true. The first line tells us that C0 is, we're going to combine it slightly differently. So if you, what I'm going to do is, I'm going to put these two together and then keep that at the end. R10, O21 plus. Okay, so what we have here is, this is the translation part, and this is the rotation part. Okay, so that formula should appear somewhere here. I think I did it right. It is, well, I did an extra step here. So here I actually took 3 frames, but it was essentially, if you just take 2 frames, then you'll see that it appears here and here. That would be the first part, and then this one will not have the R32, it will just have C2. So it's, in other words, if you take these two and combine them, you will see that the formula which you end up with is the same as this formula. So you can just keep multiplying h's, and then you will get the formula without actually having to keep track of things like this. That you need to remember how this index works. It's much more work than trying to use this notation. Okay, so we'll be using homogeneous transformation throughout. We'll always be using a 4x4 matrix to represent combined rotation and translation. Okay, so now that we've talked about the homogeneous matrix, the H, it turns out that we need to be able to use that matrix to do meaningful things. In this case, translation, rotation. So there are 6 things of interest. One would be rotation about the x-axis, rotation about the y-axis, rotation about the z-axis, translation about the x-axis, y-axis, z-axis. So how would you write that? It's as simple as this. So I'm going to write 6 homogeneous matrices now. H, X. So this X would represent something to do with the x-axis. And if I put a degree of freedom which corresponds to an angle, it'll obviously mean it is a rotation, right? So rotation about the x-axis by an angle of phi would look something like this. 1, 0, 0, 0 cosine phi minus sine phi, 0 sine phi, cosine phi, 0, 0. Okay, so what you see here is that this is actually the rotation with respect to the x-axis, right, about phi. Now, the other things over there are, well, these are placeholders. They told you 1 cross 3. These parts are actually translation parts, which will also be 0. So we can now take this and go with hy by an angle theta. We'll always use phi for x, theta for y, and psi for z. So this would be cosine theta 0, sine theta 0, 1, 0, minus sine theta 0, cosine theta 0, 0, 0, 1. Okay, now here's the thing. Remember that this is a negative. It's not a mistake. This is not an error. This is how it is. Hy is like that. Okay, and then hz psi is cosine psi minus sine psi 0, sine psi, cosine psi 0, 0, 0, 1. Okay, so that's rotation about the z-axis. And now we get to translations, which are actually pretty easy to write. So hx by an angle of, well, let's say we'll use the variable d, or if you like, you can also call it x. We'll have the identity matrix for the rotation because there's no rotation, and we'll just put an x. Okay, so the rotation part here is identity because clearly this is not rotation, it's just translation. And then the x appears here because it's translation about the x-axis. Okay, then we have 2 more. hyy 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, y, 0, then 0, 0, 0, 1. Okay, again, observe this. That's translation about y. And then finally, hzz 1, 0, 0, 0, 0, so 0, 1, 0, 0, 0, 1, 0, 0, z, and then 0, 0, 0, 1. Okay. Okay. How do you use this? Right. That's all. There's a idea homework too. I'll have a question on this. The way you use this is basically you figure out if it's translation, then you use one of those homogeneous transformation for that part, and then if it's followed by a rotation, then you use another homogeneous matrix for that part, and so on. So let me just give you an example. So if I give you a problem like this, this just shows you how to use it. It will help you to solve the problem. So here's an example. Okay, let's say that we have x0, y0, z0. And then I told you that this frame is translated and rotated to end up in a frame which looks like this. Which I should call it 1, 1, 1. Okay, so what we have is, let's say that this is actually a grid, and then you have started with the frame 0, you translate by 5 units to the right, and then you undergo some rotation to get the frame on the right. So the question is, what is the homogeneous matrix which describe this transformation? Compute the homogeneous transformation that describes from frame 0 to frame 1. Okay, so for what, so let's say that the transformation is h10, right? You need to write between, how do you go from 1 to 0? Well, first you notice that you do a translation by 5 units along the x-axis, right? So that would be hx 5 units. So when you do this translation, what will happen is this frame, and feel free to draw this when you solve it, just might make a life easy. So this would be how it will look. X1, Y1. This is the intermediate transformation, C1. So X the bar. So once it sits here, let's just draw this. Now what, let me not clutter this. Let me just, it'll be easier to just draw it here. So first thing we did was we translated it. So that is this number here, hx5. Okay, now when we did, after we did this, what happened is, in order to go from this configuration to this configuration, what needs to be done, and you can observe this, it's a 90 degrees rotation, right? It's a 90 degrees rotation about the positive z1 axis. So imagine there's a z1 axis here. If you take your right hand, you point your thumb in the direction of z1, and then you rotate by 90 degrees in the counterclockwise direction, you'll end up with this frame sitting up here, y1 sitting like this, and the z1 is unchanged. This is x1. So 90 degrees. So in other words, the next transformation you need to do is you need to do h about z-axis by an angle of pi divided by 2. Okay, and once you do that, you'll see that you will end up with this configuration. So if you want to find h10, it's basically hx5 hz 90 degrees. So we can now expand this down. I would write the formula which I wrote down from the previous page. Zero, zero, 0, 1, 0, 0, 0, 1, 0, 0, 0, and then transition about the x-axis, so 5, 0, 0, 1, and then rotation by 90 degrees about the z-axis. So cosine pi divided by 2 minus sine pi divided by 2. Zero, zero, and then all this will be 0. Okay, cosine of 90 is 0, sine of 90 is 1, 1, 0, 0, 0, 0, 1. Okay, I have not calculated this, but it's fairly straightforward to compute. Whatever you put here, I'll write it down later, but that's the answer. At this point, you can use Python, no problem. Okay, okay, so that is transformations. Any questions? Okay, no questions. Okay, so next, let's go to Euler angles.